Hello, everybody. Happy Friday. Although you'll probably be seeing this Monday, so yeah. But anyway, let's see here. So today we're going to talk about population ecology. I gave you an overview of ecology. I touched on a few things here and there. But now we're going to dive a little deeper into certain aspects of ecology because ecology is such a big, broad thing. So we're going to dip our toes into population ecology first, and then my next lecture I hope to record later today, hoping. So that way I can get everything done and up on Monday. Yes, I can do this. I can do this. Right, Monty? I can do it, right? He's like, uh-huh. Um, is going to be community ecology, which is like food webs and food chains and everything like that, and predation and mimicry. It's actually kind of cool to talk about. But this is also pretty cool to talk about. Unfortunately, though, math is going to appear. Now, am I going to, beat you about the head and ears with it? Not necessarily, but I'm going to show it to you, and I'm also going to hopefully put up a video where Hank goes over it too, and he does a good job with an example, except he uses it to find a percentage, which is not entirely what your book says or what my notes are going to say. So we'll talk about the differences when we run over that road bump. Anyway, silly thing. There we go. So let me get my laser pointer out. Laser pointer. Okay, so last time, as we discussed, when I was giving an overview of all the ecology and all that insanity, remember, a population is a group of individuals of a single species living in the same general area. So last time I gave an example of it being like all the humans living in Hendersonville right now. But why do we study populations? Well, because it can tell us how resources will be limited in one area. For instance, finding affordable houses and good jobs right now is that actually is why you could actually study population ecology for humans. It's like, why do we move from places where we're born to places that are completely different, or why do we stay? So this actually does pertain to everyday human life just as much as it pertains to us studying populations of animals out in the wild, because remember, especially in ecology, we're looking from the top down and everything's really, really connected. So there's, more than one influences going on in here. So, these studies are not just about endangered species. It's, also important for us humans for making everyday decisions. It's like, why are you going to college? Hopefully to get better jobs. So that way you can get a better job, then you can afford a better quality of life. And, I mean, basic human things we need, we want to live good lives. So before we look at how populations work, we need to define a couple of things. And one of the first things is density, which is the population is the number of individuals per unit area of volume. For instance, the density of somewhere place like New York City is, huge compared to here in Hendersonville. We don't have nearly the density that they do. And dispersion, which is the pattern of spacing among individuals within the boundaries of a certain population. Like, how are our living arrangements in Hendersonville, spread out? How does that work? Why can that tell us something about the population of Hendersonville? And, if you looked at it, we've got, a lot of farmland because of all the apples and other crops and stuff like that. And then we're clumped up in certain areas to make up for that. And you'll see that a lot in a lot of farming communities. So whereas in New York City, everybody's like, or they live in the suburbs, which is New Jersey. And don't let anybody tell you otherwise. So anyway, it can tell us a lot about what that land's being used for, how we're using it. And like I said, it isn't just for studying animals, it can be for studying human populations too. We're going to kind of yo-yo back and forth between this. So this is why ecology is kind of important, because it pertains to us just as much as it pertains to some species, of ants that we just like watching, or, Monty's population of ball pythons from Africa. Yep. Although he was probably born here in the United States, so Anyway, so how dense is dense? So, when we're looking at populations, we need to know how many individuals are in the population. How do you do this? Well, you count them. All right. And in some cases, that's easier said than done. That's why the United States has a census. It goes out every 10 years to basically figure out what the population is, how to adjust taxes according to that, how to adjust, voter registration and district lines. Technically, it should be for that, but, gerrymandering, I'm not going to go there. Anyway, long story short, yeah, we do have a census because we need to get an accurate count of the people living in our country so we can figure out, all right, which populations need more resources than other populations, and how can we help each other? Theoretically, that's what technically it's for. Anyway, with animals, it's so much easier said than done. Yeah, you can sit there and go and count, fish in a pond, kind of, except they move around, and sometimes you screw up and somebody comes up behind you and you're in the middle of counting and they talk to you and then you forget what number you were on, unless you have one of those clickers, the county clickers, like they have at Costco. So there's different ways of counting and using a little bit of math to figure it out. It's kind of like, what what is it, those jars of candy corn they put out around October, and they're like, guess how many candy corns are in the jar, and the smart kids do a little bit of math and the rest of us stare at it like, guess. And that's me. So yeah, so we prefer to do the little bit of math instead of the me version where I stare at the candy corn and go, ew, candy corn, because ew, candy corn. I don't like Peeps either, which means if you like Peeps and candy corn, there's more for you because I'm not eating any. That's all I'm saying. So, so there's several ways of doing this through different sampling techniques. There's quadrants where you set up a square and then you flop it down and then you count how many creatures you find in that square, like for instance, spiders. Which is easier to count a square than it is a huge field. And then you can get an estimate of the population according to this one square. It's like if you have a meter by meter square and you find 10 spiders in there, then if you know the area of the the whole field, you can estimate from there how many spiders are in the field from just counting out this one grid with a little bit of error. Remember, there's always a little bit of error. We always put that in to show that, yeah, this is a mathematical estimate. We're not guessing, but we're at the same time, there could be wiggle room in there. It could be a little bit more, could be a little bit less, depending on what's going on. Another method is the mark recapture method. And I've done this many, many times out in the wild. I've done this with bats. I've done this with fish. And that is what we do is we catch a few. And what we do is we mark them. And when we mark them, it depends on the species how they're marked. Like birds, you've heard of bird bands where they catch the bird and give them a little nice metal bracelet around their wrist, your foot, and then we send them off. And then if we capture them again, it has all that data recorded in the metal band number, and you look that up. We've gone a step farther with that. Instead of banding, now we've used, like, what we do with cats and dogs, or cats and dogs and other animals, pets. We put in the chip inside of them, and that lets us track big time. Gives us even more information. We start doing that with big cats out in the wild, because like trying to get them to keep a collar on that doesn't inhibit what they're doing is really hard. I mean, we made some really good, but now we just shoot a little tiny thing in them, and then we can run a scanner over them, and bada bing, bada boom, we've got all their information. We used to do that. We do that with fish too, except we do it with fish with, interestingly enough, radioactive materials. And you may be going, oh my God, why are you putting radioactive materials in fish? There are radioactive materials that do not hurt. We use it all the time. We use it to mark DNA. They're low isotopes. They don't give off much radiation at all, just enough to detect outside of normal radiation noise, because there's always radiation noise. Sunlight, for gosh sakes, is radiation noise. I walk outside, you can feel it on your skin. Guess what? You're feeling radiation from the sun. But So what we do is we put these really, really, really tiny radioactive pellets inside of them. It's in a little capsule, so it doesn't leak out or anything like that. So it's in a tiny capsule. We just shove it underneath their skin, underneath their scales. And then we can literally, when we, instead of grabbing them again, we can shove them all through a chute, and we have a machine that picks it up and counts it for us. So unless you have a bunch of grad students to make you do it for them. Yeah, that too. That's why there's grad students and anyway, or undergrad students. The biology people put you to work. Trust me, I was put to work many, many times. So I also did it with bats. And bats are really cool because we have to go find a body of water because they're going to catch the insects which come up out of the water. So what we do is we go and we catch we put up something that looks like a tennis net, but it's way finer, and the cords are very, very thin and very, very soft because anything can rip those wings, and we do not want to rip their wings. So it's like a tennis ball net, but with pockets in it. So that way they bounce off the net because they can't see it because it actually is invisible to their sonar. So they run right into it going after a bug and then fall into a pocket. And then you have to go up and pick them gently out and make sure, because they're struggling and they're trying to bite you. And remember, bats actually, especially in this area, there's only one bat that actually has the jaw strength to break skin, and that's the big brown bat. But the rest of the bats of North Carolina, I've handled, and they don't have the jaw strength to break skin. I have had one gnawing on me, and it was the cutest thing. I'm just going to say right now, it was adorable. And they're so soft. I mean, if you have ever touched a chinchilla and said, wow, that's soft, a bat is infinitely softer. They're so soft. They're so soft. And they're so cute. But anyway, so yeah, we put a little band on their foot, and same thing, because they're too tiny to stick any kind of chip into. They're just too tiny and be a waste of chips. So what we do is we weigh them, we palpate them, which is basically, if we know it's a female, we kind of feel its abdomen to see if they're pregnant and figure out if they're pregnant. It's called palpating them, which, they're probably not thrilled about because they're like, why are you smushing me? Anyway, we measure their wingspan, all sorts of get little vitals off of them and put it in a chart, and they get a number, and that number is on their band, and then we put their band on them and we let them go. And then if we catch them again, like months down the line, then we can figure out what the population is of a bat colony without having to go into the cave and count the bats, because a lot of the caves that bats live in are actually poisonous to us because of their droppings. Unfortunately, bat guano is not exactly good for our health. And that doesn't mean the bats themselves are dangerous. It's just the fact that their fumes from the guano is kind of like cyanide, so it kind of makes the air inside really bad for us to breathe unless you've got a nice respirator on, and nobody really wants to go in there and count bats because, again, they're all wiggling around and chattering and everything. So it's just easier to do it this way with a mark recapture method. And we do it with birds, we do it with fish, we do it with pretty much everything. Trying to think here, using all three of my brain cells. Sorry. There was another creature I wanted to talk about. Oh, sharks. We started doing it with sharks because we wanted to track and just how big are their territories for swimming around. And wow, we found some amazing things tracking great whites. There was actually a team, and one of my coworkers actually went out to Alaska to help with, I think it was either this or something else. He was doing mark recapture. I'm not sure if it was with sharks or something else. But anyway, he went out and he helped mark recapture animals. It's really interesting. So they actually, catch a great white, bring it up on a lift that comes off the side of the boat, and they put literal hose of running water in its mouth, and it goes out through its gills so it can keep breathing, because great whites are one of the ones that just can't stop dead, where they'll die. They have to keep moving to breathe, I believe. I'll double check that later. Watch, I'll plop up something about that, the notes in a minute. And so what we do is we put a tag marker on the dorsal fin, and it gives off radio signals. And now we're doing it with, not even radio signals anymore. We're doing it with stronger things. So we can smaller, it just looks like a cool piercing on their fin. and it doesn't get in the way of anything, but it lets us track them all over the world using satellites. So, and then we track them and we find out, oh, we've learned about females have very large territories. We didn't know that before. We could figure out, if we know more about where the sharks are going, what the sharks are doing, same thing with whales, same things with fish. We can predict better how to manage, our fish populations, how to help all the diversity in the ocean without destroying it. More information gives us a better understanding about how we can stop screwing everything up, So for the benefit, it's, for us, for fisheries, it's for, when we go, so we're not, taking so much of the population that we're giving back, that we're taking just enough. It's like why we have deer hunt licenses, so we don't over hunt the deer. I mean, we need to hunt the deer because without us, they'd overpopulate. Because we've kind of gotten rid of a lot of their natural predators, because us and wolves don't always get along. And so it's how to live with the earth without destroying the earth at the same time, because we are a very ingenious species. We're always thinking about how to do these things. So that's why we do this. That's why we count these creatures. That's why we figure this stuff out. It gives us more information for living a better life for everybody, hopefully. Now, remember, density is not a stable number. None of these numbers that we're going to be talking about are very stable. They're always fluctuating, and that's usually because there's creatures leaving and creatures joining a population all the time. So there's immigration, which I'm sure you probably know that word. It's, when a population moves around. New individuals come in from another population, same species. Again, remember, today we're talking about same species, groups of same species. We're going to talk about multi-species interactions next lecture. So, new, babies are getting born, new people move in. It's always, so that's fluctuating. That's immigration, new births and new people coming into populations. Immigration is when the population goes down because of deaths, or people are moving away, or they're driven away. And that brings me to density independent limiting factors and density dependent. So density independent are usually factors that influence the growth and the size of popularity irrespective to the population density. So this is basically how much food an area has that can support that population, pollutants in the environment, climate extremes. Like, you don't see many people living out in the deserts, or at least the crazy deserts, because not many people can survive out there. There's not a lot of food. There's not a lot of water. That's why you really don't see populations of humans just hanging out in the middle of the desert going, yeah, I like my heat, psychotically hot. So, monsoons, catastrophes such as fires, earthquakes, floods, and hurricanes. I mean, let's look at that density independent, Hurricane Katrina. I brought that up a lecture ago. That made individuals move. And people are still displaced out of Louisiana because of that, because it's just like, some people are just like, why go back? It's just going to hit us again. And it's always true. We move around due to disasters quite a bit. Katrina is just one of those huge examples of something that happened here in, our country. So it's usually physical or chemical in nature. It's like how much food you've got, how much, all that stuff. Now, density dependent limiting factors. These are biological factors that influence the size of growth, like diseases, competition, predation, waste accumulation. Like, there's an ongoing fight where all the garbage from New York City goes, and they were trying to dump it on New Jersey, and New Jersey said, haha, no. And finally, they were kicking it out of New Jersey and trying to bring it in barges down here to it was either North Carolina or South Carolina. And they found out that they had made a deal, but the people of, was it Georgia? I don't know. It was one of the three. It was either North Carolina, South Carolina, or Georgia. It was a huge to-do about 10-ish years ago, because they decided they did some deal with the governor, and he didn't tell anybody. And then all of a sudden it hit the news, and it just blew up like, like a pie in the face. So yeah, and then that completely got derailed. But there was one point, one of the three states was going to get all the garbage from New York, and we were just going to bury it somewhere in our state because we had room, supposedly. I swear it was here in North Carolina. I'll look it up and plop it up here too. Anyway, if you want to look at that. But anyway, so those are things that can also affect us as density independent versus density dependent limiting factors. And that can change our numbers as well. Like I said, Katrina cleared out New Orleans pretty good. I mean, a lot of people came back, but there was also a lot of people that just up and stayed in Texas, or there were several people I knew that came up here and settled. I had several kids that were pretty much, you can almost call them refugees from Katrina, because everything they had down there was just, and it wasn't going to get fixed anytime soon. So go live with your friends in other states. And this happens all the time. This is why we get, as a country, get influxes of people. There's people coming in because, New York's New York. Our country is kind of one of the better ones that come kind of try and get into. And that's always been, something that we've had to, argue about amongst ourselves as well. So, hot button topics, man. Biology always seems to touch all the hot button topics. It's one of those subjects that do. Anyway, but that's also why we have a lot of Vietnamese in here, because from the Vietnam War, we took in quite a few. And that's why we have, certain populations in these areas that, you wouldn't normally find elsewhere. And they were immigrations coming in. So with that said, all right, now dispersion can be different. And there's three basic types of population dispersion or distribution. So you can have clumped, random, and uniform. Clumped is usually the majority. You'll notice there's a lot of clumps. We live in clumps. I mean, think about it. There's towns, and then there's like fields and fields and fields, especially in the Midwest. It's like towns and then acres and acres of just farmland and all that stuff. And then tiny towns splotched out. And that's most common population dispersion, is like we congregate in certain areas, and then there's swaths between the towns. This reflects patchy distribution of resources in the environment. Or also with us, it's social. We are a very social species. It's actually why we have the white of our eyes. You ever wonder why we have the white in our eyes and a lot of animals don't have that? It's actually because we've evolved this because we're a very, very, very social species, and the fact that we like looking at each other's eyes. So therefore, locking onto eyes is something that for us is normal and commonplace. It's, some people see it as disrespect if you're not looking eye to eye, like you're being shifty or something, or, you're keeping something to yourself. In other cultures, it's actually too polite to look down and not look into your elder's eyes or somebody above you. So that way you're not offending them. But still, we use the whites of our eyes to communicate a lot of our emotions and a lot of different things. However, animals don't have that. A lot of animals, if they show the whites of their eyes, that means they're really, 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 really distressed. Like if horses are freaking out, they'll roll their eyes, and you'll see the whites of their eyes. Then that means they're freaking out. And never, ever, ever, ever stare in the eyes of a monkey. I can tell you this straight up right now. All the apes and all the monkeys take that as like them's fighting words. So basically, if I glared in the eye of like the monkeys, they thought I was challenging their dominance, and therefore it was fighting time. So I don't care. Do not look directly in the eyes of a freaking chimpanzee if you like living. Chimps will bork you up. Look it up sometime. There was a woman who was attacked by her friend's pet chimpanzees. They should not be pets. See what's left of her. Google her. Yeah, it's disturbing. Chimps don't mess with chimps. They're crazy. Anyway, random. So random have an unpredictable distribution. This type of species usually with individuals that do not interact strongly. So yeah, I'm not sure if I've got a good example off the top of my head for this one. I'm sorry. Maybe tigers. Tigers are like that because I'd have to go double check though. Because tigers usually don't, they're not like lions that take up prides and they actually will run each other out of their, unless it's mating season, and even then they'll run each other out of their territories just because they don't like each other all the time. So they're usually not interacting with each other unless they, want to fight or make a baby. So even then. Uniform, on the other hand, uniform are evenly spaced over the area they occupy. And this is usually where they're competing against each other for scarce environmental, such as water in a desert. You'll see this especially with penguins when they're in nesting season. And I'm not talking about March of the Penguins, the Antarctic penguins, because those suckers, that they have to stick together in clumps or they're gonna die. Now these are like rock penguins, rock jumpers. They'll spread out over a cliff and they'll make their nests and then they'll drive each other off of it, but it gives you a really uniform area of all the penguins in their nests. So you'll see that a lot with penguins living on rocks and cliffs, sea cliffs and stuff like that. They'll have a very uniform distribution. I wonder if it's like random would be a good example as Monty species ball pythons, because in Africa, they really don't hang out too much with each other. Their lives are usually what they do is they wake up in the morning, climb out of whatever hole they were in, go find a wild gerbil hole, crawl down in it at night, eat the gerbils that are sleeping, then they pass out themselves because they're digesting all those gerbils, and then they wake up and do it again. So yeah, they're probably a random because they're just going wherever they find a nice gerbil hole to go hang out in. All right, so statistical study of population dynamics is called demography. And you've probably heard this word before in talking about, the demographics of this state or the demographics of that state. Yeah, it's something we use in politics just as much as we use in biology and other sciences. So uses a series of mathematical tools to investigate how populations respond to changes in their biotic or abiotic environments. Remember, bio means living, abiotic means not living. And these tools were actually designed originally to study human populations. Now get this, the people that invented this stuff was not scientists, it was life insurance companies. And we just happened to kidnap it from them. Isn't that insane? Isn't that weird how we get certain tools from weird places? So yeah, life insurance companies came up with this to track for their own companies' information. And then biologists went, oh, that's a good idea. Give me. Isn't that crazy? So anyway, for example, life tables, which basically detail the life expectancy of individuals within a population, were again initially developed by life insurance companies to set insurance rates on us. It's like, oh, you're in a high risk for diabetes. Oh, you have to pay higher insurance. Or, oh, you live in, a place where you're actually pretty healthy. Oh, you get to pay lower insurance because you're less likely to drop dead of, cardiac disease or all that fun stuff. So anyway, the fact the term demographics is commonly used when discussing humans, but, we can look at the demographics of pretty much anything that's living. So when we're working with life tables, we usually follow a cohort. So imagine this kind of like with like all the people you went to high school with. That's kind of another type of cohort. And so it's a group of individuals of the same age from birth to death. So when they're born all the way to, when they die. And their survivorship can be represented graphically as something called the survivorship curve. And we're going to see three different curves based on the lives of certain creatures. So a plot of a proportion of the numbers in a cohort still alive at each age. And so we basically plot it at each age, how many have lived, how many have died. And we came up with, the more we did this in biology, the more we realized there's three types of life expectancies in all species, or individual species, different species, like humans versus birds. And we're going to see that right now. So all living things can be lumped into one of these three types. And the first type is type 1, which is humans and primates. We're definitely exhibiting a type 1 survivorship curve because we have a very late loss. We die when we get old, but we have a very high life expectancy in the beginning because we give so much to our babies, because our babies are very much helpless. So we put a lot of time and effort and resources into making sure our babies survive to adulthood. We're also known as a K-selected species because of this, and we'll get into K and R select species in a minute. So that's going to come back. This topic kind of goes in a circle. So there's a lot of parts I'm talking about that I'm going to come right back to a little bit later, and you're going to be like, didn't you just talk about that? Yeah, because it's kind of a circular subject. Like the way your book kind of breaks it down kind of annoyed me in the fact that I was taught in a different way, but it's still the same circle. It's all one big circle. It's like, the Ouroboros, the snake eating its own tail. That's how I feel population ecology kind of is. It's all this, all the information of what it is kind of feeds in on itself. Hey, Monty, have you ever thought about eating your own tail? No, I'm not stressed out. Yeah, actually, stressed snakes will chew on their own tails on occasion, but Monty is, as you can see, the opposite of stress. Boy, must be nice to be a very well-kept snake, right, Monty? Yeah. So anyway, type 1 survivorship, where we basically high survivorship throughout life. Majority of us reach maturity because we put in so much effort into our offspring. And then, as we get older, that's when we start dying off. That's where you see this drop off of survivorship. It's like high, because we want to make sure our kids grow up, and then dumps off. So humans, elephants, other of the primates, annual plants. So it isn't just, plants and things, or humans and things. Anyway, so type 2, on the other hand, has kind of just a straight slope. And the reason is because it's a constant loss. For every birth, there's always a loss. So it kind of equals out and then dumps off. So basically, because birds die more or less equally at each age. So they have few offspring, provide parental care. Birds have to teach their babies how to fly, which I saw one time. We were sitting out on my porch, and a mom was trying to get her kids out with some food in their beak, and it was funny because it was time for them to fly, and oh god, it was like watching these little puffballs going. It was so funny. Funniest thing. They finally figured it out after a few attempts because they were chasing mom around because she had breakfast and they were hungry. But oh god, it was pretty funny watching them take their first flights, which was more like going like wee. So a lot of creatures, birds, rodents, hydra, perennial plants, they have equal loss at each age. So that's why it's pretty much a straight line all the way down. Now, what? Hi. Anyway, type 3 survivorship is basically where they make a ton of babies, and there's not really any prenatal care. They're just like, you've been born, good luck with that. Kind of like sharks. Sharks do that. Sharks usually just give birth and are just like, bye. So can you imagine? It just feels like you have indigestion one day and all of a sudden you kick out a bunch of babies and you're like, and then you move on with your life. I don't know how that works because that's not how humans work. But anyway, but yeah, so these guys have a ton of offspring that they don't expect everything to survive because there's just no way. So they put all their literal eggs in the make as much as you can, and hopefully some of them will survive, and that's that. So unless these offspring are literally on their own or vulnerable to predation. So that's why the sheer numbers assure survival, because they just make tons and tons and tons and tons and tons. So oysters, small fishes, trees, sharks, anything that just literally produces kids out the wazoo. Shrews are definitely, shrews are weird. I've caught shrews. They are psychos. They literally come out, they're born literally ready to get pregnant. I mean, you thought, teenage pregnancy's bad with humans. Shrews are worse. And that's because they have a exceedingly high mortality rate. They don't live very long because their metabolisms are so crazy high. They have to constantly eat their own weight, like every 10 minutes, I think. Something like that. It's insane. Yes, it is. It is insane. Yes, Monty. Yes. Yes. What are you doing? Okay. So anyway, shrews are weird. Shrews are so weird. Anyway, freaky little creatures, but they're a type 3. They literally come out ready to go to have babies. So that way, more babies, more survival. Party on. So those are the 3 types of survivorship curves. Type 1, which is, lots of prenatal care. We make sure our babies survive into adulthood, and then we drop off with old age. Type 2, where basically it's a kind of even death rate going on and down. And type 3, where there's a huge death rate at the beginning, and then once you hit adulthood, you can live for quite a long time, like trees, because you've made a whole ton of babies and hopefully somebody lives. So species life history describes basically a series of events over its lifetime. So resources allocated for growth, maintenance, reproduction, and life history affects the life table as well. And this is basically genetically determined, shaped by environment, natural selection. Like I was talking about that one last time, that one hummingbird species that can only get food from this one plant, and that one plant can only be pollinated by that same hummingbird. So they're a 1-to-1. So if something happens to them, that's going to screw up the life table of the hummingbird population. So now we have something called an energy budget. Yeah. And just what you thought, oh God, me paying bills, I have to pay energy bills too? Yes, you do, because we Duke. Anyway. And anyway, they must balance energy intake with use of their metabolism. So in other words, they've got to make sure that they've got enough energy to have kids in the first place and make sure they survive, as well as they themselves surviving. Like bears building up body fat for winter hibernation, although it's not exactly a true hibernation. It's kind of like spotty. There's a technical term for it. I can't think of it. I know we've always been like bears hibernate, but yeah, and they do. I'm not saying they don't. I'm just saying it's not the true hibernation like those frogs, those wood frogs I showed you that just freeze. That's considered true. There's nuances in hibernation. I don't think we're going to get into them in this course, though. So sorry about that. It's kind of interesting, though. But anyway, we need energy to do these things. And if you can't feed yourself, how are you going to feed a baby? That's something we've all been screaming for years when we hear about such a whoozy watsits and they have a baby and they're like, dude, they don't even have a job. Yeah, it's like that, except it's with energy resources in the animal world and the plant world. So, there's still a budget. There's still where we have to figure out, okay, do I have enough energy to survive and have kids? So fecundity is basically the potential reproductive capacity of an individual within a population. Another, how many kids can you make? Like I said, with us humans, we don't make that many kids unless you're Octomom, who was hitting the fertility drugs for no reason. No, she wasn't even infertile, I don't believe. She just liked hitting those drugs, and the doctor kept giving it to her, and it's like, oh. Anyway, I'm sorry. Just no. There's just not enough room in me to do that. I've already had one kid, so. Anyway, so in other words, basically it describes how many kids can be ideally produced if the individual has as many offspring as possible during reproductive cycles, and then taking care of it after birth. So it's inversely related to the amount of parental care given. So you'll notice that the more, like if you go back here to the type 1s, We don't have that many kids because we put a lot of effort into making sure the ones we have are cared for and can go on into and survive into adult. So you'll notice those of us, so we have a very low baby ratio compared to how much energy we put into making sure it survives. Whereas type 3s, on the other hand, they make a ton of babies because they know not everybody's going to survive, and that's how it is. So, sharks give birth and swim off and big good luck to you, man. So we don't, they don't protect their babies. They don't do anything like that. They're just like, good luck and Godspeed or whatever. Anyway, you know what I'm getting at here. So that's why it's fecundity is usually inversely related to parental care. So now, animals that have few offspring usually means we have extensive parental care, like ourselves, because let's face it, our babies come out extremely helpless. They can't even lift their heads because their brains are so big. And that's how we went with that, becoming a type 1, because we need big brain to live. And unfortunately, the trade-off is we need to take care of big brain baby that can't move big brain, because big brain is huge. So big brain problems, you know what I mean? Sometimes I feel like my brain is shrinking, but anyways, this is a case with most mammals, humans, kangaroos, pandas. That's why we, give birth. Now, rabbits, on the other hand, they're just make a ton of babies. But again, they still have to take care of their babies until they can hop off themselves. So they still give parental care. They just make a ton because they're a prey species. They have to keep up with, the fact that they're getting picked off a lot. So again, we'll get into that more when we talk about communities, because this does feed into community ecology as well. How many babies you make because you're a predator species versus a prey species. Like I said, all of this is very much together and smushed together. Like I said, that circle that kind of feeds back on itself. And it's also, imagine the Olympic rings, how they're all interconnected. It's kind of like that with ecology. It's like these are very interconnected, but I'm trying to split it out so it makes sense to you, because it's hard to jump in. It's kind of like physics. Physics is the same way. I had a physics professor that told me the first day I took his physics course that the only way to understand physics is to understand physics first, which is like, if you don't know physics, then it's like a catch-22. And he was right. After I took physics, I realized I understood more of where we began in my first physics course than at the end of the physics course. And I was like, oh, that explains this. It's like a loop that feeds back on itself. So that's physics. That's ecology. There is no beginning. There is no end. It's forever. Right, Monty? He's like, what? Anyway. So timing of reproduction also affects species survival. There's some creatures that have, babies at an earlier age. It's actually one of the reasons why we actually can get pregnant before we're adults. We're one of the rare mammals that we don't have to hit adulthood to have kids, which of course brings up its own issues. But that's one of the reasons why, is because life expectancy before the Industrial Revolution was around 40. So I'm 43, so I would be an old woman like 100 years ago. Yeah. And that's why they married off women younger, because, they were younger, they could survive giving birth, even though they weren't true adults yet. Although now we do research and it shows that it, messes with things. But we can, and that's because we have to put so much time and effort into raising our children. And even before the Industrial Revolution, we lose the majority of children really young, quite often. It was, what we think is unthinkable these days. Back then, it was almost normal to have. That's the reason why families had lots of kids. I mean, go back through the wiki and follow like a royal family and just see how many kids died before they even hit adulthood to have my heir inherit the throne. If you look at some of those death rates, like Catherine the Great, go through how many kids she lost, and how many kids she had. And same thing with her kids. And then, you know, even before that, it's really interesting. You know, even royalty, who got, you know, the best of everything, including medical care for the time back then, they still lost kids quite a bit. So yeah, industrial revolution, our population really took off. But anyway, getting back to this, so you know, organisms that start reproducing later in life have greater fecundity and are better able to prevent the too many P's to provide parental care, but at the risk they will not survive to reproductive age. So and timing has a lot to do with a lot of this as well. So anyway, so that brings me to basically, let's talk about family planning in certain species. So we've got seminal parity, which is basically when a species reproduces only once during its lifetime and dies. They use all of their energy budget on just making kids and then moving on. Bamboo is one of this, because bamboo will flower once and then die. Salmon, you know, they do all that. They jump, you know, after all those things where I showed you the salmon chute system, that whoosh system, and they go, boom, or the salmon ladders, they do jump, 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 jump. They all have sex and then they die. Of course, it's not maternal. It's just ladies lay eggs and the boys release their sperm all over the eggs, and there you go, you know. But then they drop dead because they wasted all that energy coming from the ocean, jumping, 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 going to their spawn spots. But interestingly enough, their rotting bodies usually give nutrients back into that area, so that way the eggs survive. So that's also, you know, part of it, to make sure octopi do the same thing. Heck, who's read or watched the video Charlotte's Web? You know, a lot of times the female spider will die after she lays her eggs. A lot of insects do this. So that's a semiparity, which is basically we save up our energy budget to have a bunch of kids, and then we use all of our energy to protect them, and then we die. And that's just how it's done with like octopi and spiders and salmon and bamboo. And so again, that's why we all cried at Charlotte's Web. We're like, oh, please don't die because she's having babies. So listen, I cry at the drop of a hat. All right, I'm a big weenie. You know, Pixar movies will always make me cry. That's why in my family we have a saying, "Damn you, Pixar," because they make me and my husband, we're big softies, okay? We just cry. We're very in touch with our emotions. Anyway, right, Monty? He's like, what? I don't cry. You don't have tear ducts. Anyway, so interoperity is on the other hand, is basically a species that can reproduce repeatedly during their lives. Some of them are only able to mate once a year because of cycles and heat, going into heat, not like with dogs and cats. The pronghorn antelope, he goes into a seasonal estrus or a heat, and that basically induces them for successful mating. So females of these species only mate during the estrus phase of their cycle. We don't have that. I know we have a time of the month, but we really don't have that. There is no heat. There is just, hey, our body is ready once a month to get pregnant if everything's working fine in your body. So anyway, so, you know, and different patterns is observed in primates, including humans and chimpanzees. We can get pregnant anytime during our reproductive years. And menstrual cycles make it likely for only a few days during the month. So we have a monthly shot at getting pregnant every month. And, you know, and we can survive having multiple babies. And although we're designed to usually have one at a time, sometimes 2 or 3. The rare, you know, groups are usually these days done with somebody's been doing the fertilization drugs a bit too much and dropping too many eggs at once, because that's kind of what it does. It kind of accelerates you dropping eggs. Some of the drugs, not all of the drugs. In vitro fertilization is a whole nother potato we don't have time to get into right now. Anyway, where was I? Right. All right. So this brings us to growth. So Charles Darwin, and I talked about our boy who was depressed, was greatly influenced by the English clergyman Thomas Malthus. And Malthus basically said that if populations are giving everything they needed, they represent very exponential growth. And you can see this, like this picture right here of bacteria just going crazy. If you give them everything they need, they're just going to grow, 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 grow. And it gives you that exponential curve that if you've taken math classes, you've probably seen him before. And that just means that we start with a few individuals and then just population explodes because they have everything they need to just make more, 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 more. Now, when resources grow depleted, though, you'll get an S curve. So this is called the J curve or a hockey stick curve with exponential growth. That's if like everything's perfect and, not a lot of creatures are dying and nobody's predating and everything. Because when we get into predation rates, you're going to see these two basic graphs change big time. Next lecture. So you get this S curve, so Y S curve. So that's the carrying capacity right here. Cuts you off. And we'll talk about that right now. So we get formulas for this. So if we take the bacteria example, some bacteria will die and not reproduce. So to figure out basically the formula for, organisms that die, organisms that are born, and what's going on and how the population is changing, you'll get this formula right here. So you take the birth rate minus the death rate, because you have to count for those things. And then N is always population. So N's your population. So say you have a population of 1,000 individuals, okay? And T is for time. Now, the delta symbol in science, I say this often, I believe I said it in this class too, delta always means change. So if you see that triangle, it means something's changing. So if you take the original population number over the time, that you're watching this certain population, it should equal the birth rate minus the death rate in that amount of time. And this is the basic formula for figuring out what, how your population's changing. So then we can actually stick some other things in. And this is where it kind of like, if you're not a math whiz like me, you start going, oh God, my eyes. And yeah, so let's go ahead and look at this. So sometimes its birth rate is based on per capita. So the B, the birth rate, and BN is the per capita rate. So again, we're not getting perfect numbers here. And again, number of individuals in a population is N. They love, so whenever you see N, that's the population in here. So, but anyway, so this part gives you instantaneous growth rate. I didn't mean that. No, go away. Shoot. So this means instantaneous birth rate right here, which is basically replacing the number and the time with interspecific measure of time. So birth rate minus death rate. Again, you can just take it and move it around because math is fun like that. So you just put it in parentheses, birth rate minus death rate times the population number. Again, am I going to make you do this too terribly much? No, not really. I'm just letting you know what the heck all the numbers mean in the book. But I'm not going to go crazy on this. This is not one of my, let's go crazy. Now, calculus. So D is associated with the first term that means derivative. Calculus, here we come. And it's different from the death rate, which is also D, because, you can't have enough letters that are exactly the same to make this even more confusing. So the difference between the birth and death rates is further simplified by sticking in R. So getting that number of the birth minus the death rates, we'll just slap that in and call that R. So the value of R can be positive, meaning if R is positive, that means the population is growing in size. If R is negative, it's decreasing in size. So, however, there is a weird condition called zero population growth, where basically the size is unchanging, and it happens. So it's basically the maximum growth rate is called the biotic potential, or Rmax. So that's what this Rmax rate is. So that is basically the maximum a population can go, looking at all the different things that are limiting the population. So remember, a bacterium can reproduce more rapidly and have a higher intrinsic rate of growth than a human. I mean, that's, literally you can do that with a petri dish here, in class. I can give you a petri dish, and you can just stick it in a warmer, pull it back out the next day, and you can see the population just exploded on there. So, some creatures move a little bit faster than others, but, the petri dish is their whole world. So once they run out of all the agar to eat on that petri dish, then bada bing, bada boom, all of a sudden the population is dying off because it's run out of resources to eat. So unlike us humans, we try to figure out new ways to feed ourselves. So the bacteria don't set up research laboratories and try to figure out, okay, how do we get out of the little petri dish? Because that would be bad. Anyway, so that's a biotic potential. It's what's your maximum growth rate that you can sustain without exploding? If that makes sense. Hopefully that makes sense. So in the real world, with limited resources, on the other hand, exponential growth cannot continue indefinitely. We're hitting that too, because if you look at a population growth for humans over time, we literally go flat, 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 and then we explode with the Industrial Revolution and have huge, huge J curve. And then we go into an S curve, and that's where we're at right now. Apparently, we've leveled off because we know we're kind of at our carrying capacity, and we're trying to figure out ways around it, but it's keeping us kind of even at the moment. Plus our own economics. Economics does have a role right now. That's why, the older generations, when we sit there and say, okay, boomer, I'm an elder millennial, so, I've been looking at this from half a perspective of millennial and half a perspective of the end of Gen X. So, when they bug you and they're like, why aren't you having kids? Why don't you have a house? Because nobody can afford a house. Anyway, different thing, but again, touches on this a bit. So anyway, so the carrying capacity is, we will designate that with K. Why K? I don't know. Nobody talked to me about these things. So the formula we use to calculate logistic growth adds carrying capacity and moderate growth rate. So the expression K to N indicates how many individuals may be added to a population at a given stage, and K minus N is divided by K, which is a fraction of the carrying capacity. So this is basically how carrying capacity restricts us. Now, one of the things in the math right here, I want to kind of slightly point out. So notice that when N, so if N is very small, if you have a very small population, and this K minus N divided by K becomes close to 1, that means the population is growing exponentially and is not influenced by a carrying capacity because they haven't hit it yet. Okay. However, on the other hand, if N is huge, like you have a huge population, and this part right here comes close to 0, that means the population growth is slowed or stopped, because that's where the S-shaped curve and the carrying capacity hits us, where we've hit a limiter of something, like we don't have enough water, we don't have enough food, and it limits us from taking our population any higher. So that's basically what this math equation is trying to tell you. It's, is this how the carrying capacity is affecting the population at the time? Is it an exponentially growing, or is it hitting that top of the curve, of the S-shaped curve, because they've hit the limit of all the resources that they can use to carry their population upwards and onwards? So that's what I'm trying to point out with this math. I'm not sitting there going, I'm trying to help you see that, what this means, and not, oh, okay, it's just a bunch of letters all hanging together and calculus is doing its calculus thing. All right, that brings me back to, hey, remember this? Yeah. So this brings me to K-related species versus R selected species. So depending on all this fun stuff back here, so remember K is carrying capacity and R is, the birth minus death rate. And that brings us to species that are selected either by their, limited by carrying capacity or limited by birth minus death rate. And you'll notice this overlaps with the lifespan graphs I showed you earlier. So K-selected species like humans, again, we put in all that work to make sure that we get our kids to, adult stage, so then they can go off and live, hopefully, theoretically. And our selection, where they make a ton of kids and hope some of them survive, and then they live for a long time. And the ones that survive. So they have very early high death rate and then even out into a long lifespan, or very, very low death rate at the beginning, and then they live a lifespan and then die off rapidly as they age. So again, K selected is type 1s and R selected is type 3s. So remember when I said we'd be coming back to that? Here we are. So that's actually showing in the math right here. So we are a K-selected species. We react to our carrying capacity. And one of the things you can actually see this is actually in humans, this has huge implications for inter-country insanity. Like, for instance, Al-Qaeda. Where Al-Qaeda came from and where they pick up all those disgruntled people that, hate everything but themselves. Where do hate groups come from? Well, it's actually one case, in this case, it was because there was a drought in Syria. And the drought in Syria destroyed a lot of the farms. So farm families lost their homes and they had to move into the cities because there was no water. And because of this, there was a lot of young men hanging out because there was no jobs for them because the farms had all dried up. There was no factory jobs. That was at a premium. So what does a bunch of young men loitering around with no purpose in life, nothing to do, can't feel hopeless? They get upset and they're prime pickings for hate groups. So that's a carrying capacity thing. That drought basically caused groups of people that cause terror or that become terrorists. So yeah, a drought can actually drive human populations to do extreme things. And that's something we need to watch from an ecological factor, which factors into human behavior and whatnot. So these are things like this. It's like, where did they come from? Well, it happened because this huge drought was happening in Syria and made a ton of disgruntled people that were easy pickings for hate groups to pick up and make their members. So yeah, so we're a K-selected species. So we exist very close to our carrying capacity. Whereas our selection, they don't really hang out too close to their carrying capacity. They put out as much as they can to survive, and they usually equals out in the end to what the carrying capacity is. So their birth rate and their death rate kind of overcome each other. So that's why there are selected versus K-selected. Does that make sense? I hope that makes sense. Again, it's how much offspring can we make? Like chimpanzees can have 2 kids a year. Large cat can have 2 a year, 2 litters a year. Not always, but they don't always do, keep in mind as well. Hares, 200 a year. Cats and dogs are up in here too. Frogs, 200 a year. Fit, tuna, 6,000 kids a year. Fun. Oyster, 500 million a year, but only a few live to be an adult. So interesting. So again, you'll see, the ones that put out more and more kids are R selected, and more and more less and less kids are K selected. So see how it's come right back to itself? Yeah. So what about humans? So our population is growing rapidly, long-term exponential, we carry the risk of famine, disease, large-scale death. Because we always, like Katrina, where there's, days Mother Nature's going to throw curveballs at us. And yeah, we study that to make sure we can be more prepared. Like, that's why we study earthquakes so much, because we don't want what happened in San Francisco to happen again. The Great San Francisco quake of 1804 3? Question mark. It's 3 or 5. But we're due. We're really due. But anyway, but that's why we have all these things to like. We have a sensor network in the ocean to predict tsunamis. So that way, you know, when a tsunami nails Japan, they're forewarned that it's going to happen. So they all run off and, you know, away from the coastlines and batten down the hatches. So we're trying to do our best to, you know, predict these things like, you know, hurricanes, so we know it's coming, so we can get out of the way, but it doesn't always work the way we think it does. And earthquakes, sometimes earthquakes just earthquake wherever they feel like earthquaking that day. Like the one we had here, was it? We had one last year. It was pretty, or was it the year before that? We actually are on the Linville fault line, so we do get earthquakes here. Not that Monty would notice. No, you slept right through it, didn't you? Anyway, so human population is currently experiencing exponential growth, though we're actually, our reproduction purposes are way below our biotic potential, which is a good thing. So to reach biotic potential, all females would have to become pregnant every 9 months and have kids until they weren't able to do that anymore. That would be biotic potential. Aren't you glad we don't do that? I am. Anyway, so all resources would be have to such that would support this such growth, and basically neither of these two conditions exist. So we're not like bacteria. We're not going yeah. We're like, yeah, no, I don't know if I want to have kids. You know, we have there's a lot more into it than just, you know, what all these numbers represent and all this stuff. So even despite this fact, though, our population is still growing exponentially, and we're always trying to figure out new ways to push our limit up and up and up. And we've started really working on that, like with the 3D printed food and, you know, all that fun stuff. Now you can look at this, it's called an age structure, and you can see this population dynamics, especially if you're looking at countries. So if you look at the birth rate versus death rate, so that's what the two colors are. So the blue right here is the birth rate. The red right here is the death rate. And if we stack it up by age going this way, like, you know, age 1 to 65, and we do it for every cohort, you know, in the population of, say, the United States, this is actually what you'd see for the United States. We're stable. In other words, you see that we're very stable in age ranges going up. And then, you know, after 65, that's when we start losing our population. Where developed countries are usually in a stable age structure diagram right here. Although there's other developed countries that are in declining, like Japan's really bad about that right now. Japan's declining. They're making less and less kids, and their older people that outnumber that are not there to replace. So they're experiencing a major population decline, which is actually worrying the Japanese government right now. Another one that's basically declining would be Italy. Italy's having 0 population growth. So they're more conical. So this would be Japan. Slow growth would be probably, this is Italy right here. Less developed countries in Africa and Asia would have the rapid growth, like Kenya. This would be Kenya right here. You'll see that in less than developed, so they'll have more of a rapid growth rate. So that's basically age structure. Kind of tells you, you know, how is a country using its resources, you know, what's happening in that country based on, you know, the individuals of certain age for each cohort. And what does that tell us about, you know, the stability of said country? So it's kind of an interesting look at these things. Yep. Yeah, I'm going to turn this hopefully into something you can watch, the H5P thingamajiggy. So I'm going to be working on that. So.
And our series on biology took many weeks to get.
Hank, shush. Now, last thing I want to talk about something weird, because you know me, I've got to talk about something weird. So, once upon a time, there was a ethologist named John Calhoun, and from the 1950s to the 1970s, what am I saying? He studied rats and mice, And he was trying to study population dynamics, but he was doing it by making a perfect utopia for rats and mice. And he'd call them like universe this, universe that. So he'd build these huge structures. I mean, this is him in the middle of one of the utopias, and it would give unlimited food, anything the rats needed. So they'd have these little, like, in between all the food right here, they'd have all these nice little dens they can make families in. And they'd make these different levels, so they'd have infinite food, infinite water. They didn't have infinite space, but they had, they're protected from predation. Nothing was killing them other than natural causes. So he made these things, and he studied these morality inhibiting environments for mice. So he basically, like I said, he made these ultra habitats so the mice and the rats wanted for nothing. Now, he was working with the National Institute of Mental Health. Notice the name of when you abbreviate that. If you are a fan of a certain cartoon movie or books, you probably are going, what, right now? And I'll get to that at the end. So tip off. Now, what he did is he basically would let the universe go. Now, his most famous experiment was with mice, and it was called Universe 25. And basically, he threw in, like, I think it was like 20 mice to start with, and the population peaked at 2,200 mice. And they started, their society and their behaviors started to break down because they didn't have to compete for food. They didn't have to compete for water. There was no competition. There was no survival. So it got really weird, including, like, courtship would break down between the males and the females. And the females, if they got pregnant, even then the pregnancy wouldn't go through, or they'd have babies and they'd just leave them everywhere. They'd forget their babies everywhere. Literally their behavior was starting to break down. The boys, there was one that was pretty strong, and he used to sequester off mice that he liked the look of, and they were called the beautiful ones. And they were all in, like, one corner while the rest were all, like, eating each other. It was insane. It was literally insane. So mouse society was breaking down in Universe 25. By the 600th day, the population was on its way to extinction because the females had forgotten how to take care of their own kids. Even though they were physically able to reproduce, they had lost the social skills to mate. They'd just attack each other. And so so these studies were really interesting, but unfortunately it led to a lot of people going, oh God, this is what's going to happen to the human population, and we're all going to die, and society will break down, even though we want for nothing, and oh my God, and we're going to start killing each other, and like Mad Max, kind of movies, stuff like that. We're all just going to go crazy and start wearing leather and spikes everywhere and soup up our cars and drive around and be weird. No, actually not, because we're insanely social. Mice are social, but mice are also a pain in the butt. I know I've raised at the zoo. We had our own mice breeding facility to feed all of our snakes and stuff. And I'm going to tell you right now, mice are nasty. Rats are smart and wonderful. Mice are nasty. I'll get into that rant another day. And anyway, nasty. So anyway, so there's a lot of people that took a lot out of this and went, oh my God, our society will collapse when we hit perfection. And it's like, not really, because we're always pushing against ourselves. We're not exactly an animal, we're in the animal kingdom, don't get me wrong. We're genetically, we're one hair off from a chimpanzee, but at the same time, we don't, we're very engineering creatures. We're always, looking, asking questions, looking why, you don't see Monty doing research on other snakes, and we're always coming up with new and interesting information. We're always looking. These mice, they weren't doing any of that. You didn't see them build like a nice school to teach their kids or anything like that, or stuff like that. So there's some interesting information to be taken from this, but at the same time, a lot of people, when he published this research, a lot of people lost their minds and said, oh my God. And that's where a lot of the doomsday stuff came from the 70s on up. is taking notes out of this research. So it's kind of interesting, but interestingly enough, and if you haven't clued in yet for me pointing this part out, this is actually where the author of the book, Miss Frisbee and the Rats of Nim came from, which later got turned into the movie The Secret of Nim. NIM literally is the National Institute of Mental Health. Now, they're not some jackboot thugs that you saw in the movie trying to do weird experiments on rats and mice. And yeah, they were doing some experiments on rats and mice, but as you can see, they were setting them up like that. They weren't injecting them with smart juice and making them. Don't get me wrong, I love that movie. I love that movie to pieces, but that movie is actually based on actual scientific research. The movie and the book are based on this. Isn't that interesting? So there you go. There's my weird story for today, the mouse utopia studies. Look it up sometimes. Really interesting that how much the mouse behavior degraded. It was really interesting. And of course, The Secret of Nim, one of my favorite movies when I was a kid. All right. With that said, that's all I've got for you today. I'll probably get this up hopefully on Monday, and I'm going to try and record another lecture a little later today. So hopefully you'll have another one up on Wednesday. Jumping off here, we're going to now talk about interactions, because unlike these mice in Universe 25, nobody lives in a vacuum on this planet. We have to interact with a whole bunch of other species, right, Monty? Yes. So that's what we're going to talk about next. Populations interacting with each other, which is community ecology. And with that said, you guys have a good one. Take care, and I'll talk to you later. Bye.